Hey guys, so we need to talk once more about this battery spot welder I showed in one of my last videos. And in that video I complained a bit about the display being the wrong orientation, like 180 degrees rotated. And if we now turn it on, let's take a look at this. You can see the screen is now rotated to better work with it. And this video is to show a bit the way I got there, with a bit of a plot twist in the end, so stay tuned. But on the other hand, I want to try to make this video as deep dive as possible to really show what goes into reverse engineering the insights, so like dumping the firmware, reverse engineering the firmware, and finding out what is going on with the screen. So it will most likely be a very long video. If you like such stuff, keep watching. Otherwise, just skip to the last segments and you will see the solution to all of this. And yeah, have fun. Let's take a deep dive into reverse engineering with IDA Pro. So to give an overview of how I handle such reverse engineering, what is my way of it, we first need to get again inside of this spot welder. And since this is such an uncomplicated target with no fear of getting into troubles of showing this procedure, it's the best way to show it to you guys. And first of all, we of course do a tear down again and get the main PCB out, since the first step is always getting the firmware out of the microcontroller, with the hope of the flash not being locked. Spoiler, it's not. If it would be locked, then it's a way harder story, but yeah, this is where it starts. After tearing it down, I looked up the datasheet for this chip, this HK32C030, and first of all saw it's a Cortex M0 chip. This is important in a while for the later reversing, but most importantly the pinout of the chip to see where the programming connectors are. So most of the SDM or SDM clones use this SWD interface, and you can see that we have this SW clock and SW digital in and out. And if we then take a look at the PCB and rotate it the right way, we can see with a bit of zooming that the first trace here, this SWDIO, it's the third pin on this row here. Let's try to focus. It's here, 1, 2, 3, and we can see that this is basically this wire going here. It's not so nicely named, but yeah, in the end this is a debug header nicely prepared for us to solder on our flashing device. And after that we can take an SWD flasher. It's like, I'm using the Sega Flasher Pro. It's quite expensive, but also it holds its value. You could also use such like a €2 SD-Link clone, or even a real SD-Link and such. To do the same stuff, I will now use the Sega, as it's, why not? If you have it, it's the best. So I will connect the wires of the SWD pins to the programming header, and let's see how this goes. So you of course also need a soldering iron for that, but that also depends on your setup. It's just to show the full way. Let's quickly wait for it to heat up. And I will just simply solder the ground wire onto the debug header. Since it's pre-tinned, it's quite easy now to just reflow the connections. Then I will connect the clock pin and the DIO pin, or the data in and out, like so. And VCC is also needed, especially in the Vega devices. This is switched later from the programmer. Usually you would have like here you have like 3.3 volt output always on. You could also use the internal battery for VCC, but the Vega is always checking if the voltage is even there to connect to the device. So this is basically it from the hardware perspective to dump out the firmware. This is of course different also to a lot of chips, a lot of devices. SWD is quite nice as it's just 2 pins and universally used on many devices these days. On the PC side, I will open the JFlash application. It's the official Vega application, and we want to get a new connection. But to do so, we need a new project. And it's important to notice here we have a list of quite a lot of devices already. But since this chip is not supported by Vega, the way would be to either use the SDM, the real device, or like just use the Cortex M0 one just to have a basic SWD connection. If you ever come across a chip that is not at all in the list or not a direct clone of something. We want to use the SWD connection. We do not save the old project. And then what we want to do is set the power output of the Sega flasher to on if we want to connect, as this is not always on. After that, we should be able to connect to the chip. And as you can see in the log here, the connection was successful. And right now, with only having a Cortex M0 chip selected, it does not know about its flash, its memory. So the way to go now is to use this J memory and also select the Cortex M0 chip here. It will then use the same connection as it's already existing in the background from the JFlash software. And voila, we can already see some bytes already here. There we can scroll down a bit. It will actively reload from the chip the memory, and we can see how much flash is used at all. So we can see that here roundabout there it's just FFFs any longer, and we want to have this data extracted, so we just copy it in this case. There's also an option to export it, but why do so if it's also possible this way? Let's do it that way then. So by scrolling down, marking every data we want, like so, and I hit Control and C to copy it. And let's open up the hex editor if I would have it installed here. Okay, like so. And this HXD Explorer is quite the nice tool. It's very universal for hex and bin files. We want to now copy in here the data. That way we have a dump of the full firmware. And in theory, we could even disconnect the hardware already and put the device back together if we do not want to flash something different onto it. But let's see how this goes. This file can now be saved, just like on the desktop or somewhere. And let's call it Spot Welder dump.bin. This will be opened later by IDA. So let's close that already. We can now see here, just as the more infos, that the flash is from the address 0 and up. And mostly RAM addresses are at this address, so a 2 and 7 zeros. And if we go there, we can also see that there is data. And if I scroll down, we see that it's getting to much more randomized data. So we see that this is where the used data stops already, and this is like garbage. So most likely the firmware is initializing this part here, but nothing more. It's just for ARM Cortex devices, a general info. And if I would now try to scroll down way further, we see that it stuck. I'm normally scrolling further. So here the microcontroller is not answering any reads of the memory addresses anymore. So we know there is just no data anymore at that place. But let's close all of this and continue with this file. Since we do not need the hardware anymore, let's turn that off and switch to IDA in a moment. So after having the firmware dump ready here on the desktop, we want to open it up in IDA and taking a look inside and reverse engineering. What IDA is, it's a software reverse engineering tool and basically the same as Ghidra, which is the same but an open source tool. IDA is paid to win, so it's up to you what you choose. For the beginners, I would use Ghidra to get into it. Personally, I live in IDA and it's just working best for me. So this firmware file, we now want to open it just by selecting it as a new file. And since we earlier saw that the processor is an ARM processor, we want to use ARM as well. And 99% it's little endian. It's like how the bytes are rotated inside of it. So we select it here as well. Inside of everything, we could also now set here more settings of what exact architecture we have and what some code and such is. And we will leave it at the default settings. So we click OK. After that, we can create the memory regions. And we did saw earlier that we have RAM and that it does start at this 7 times 0. And the size was roughly like 700 in hex. Now to the ROM section. While the memory did start at 0, so we saw or dumped it from 0, on the STM devices, this is mostly mapped to a different region in the processor itself when it's running. If I'm now able to open up the image at all. Let's do it this way then. I have prepared it on a different section here. So we can see that the flash itself does not start at 0, but it starts at 8 million. And we can also verify this by opening up the flash dump, and we can see that the beginning here looks very similar in the content, and every 4 bytes are basically repeating more or less. This is because this is the interrupt vector. It basically tells the processor on where to jump to if a special interrupt occurs, like if you have a timer interrupt or an GPIO interrupt or SPI interface interrupt and such. So, and on the ARM processors, it starts with the RAM section where the stack is laying. So this is the first 4 bytes. But after that, we have these 4 bytes of the reset interrupt vector. So when the chip boots, it will first look here where to jump and go there. Since it's now little endian, we need to rotate these bytes. So it starts by 08 0000 D5. And if we convert this, it's like this 8 million again. So back in IDA, we know really that the flash is starting at 8 million. So 8 and 6 times 0, like so. And we also need to select this in the loading address. So IDA knows that the file should move by 8 million and also that our ROM is moving by 8 million. After that, we can just open the file. And we see it's still quite ugly. So we still only have all the bytes. And based on that, we know we have these interrupt vectors. At the beginning, we can directly change this to uint32 data, so 32-bit data, by pressing D in IDA. So you can see that the numbers get created correctly. This is all now just preparation for the later real reversing and just shows what to do. Another thing is that we need to change this code 32 to code 16. We can do this quickly by pressing Alt and G and changing this value to 1. This will make the interpreter look for some code, which is ARM short code. It's basically like normally you would have 4 bytes being one instruction, but ARM does it that you also can use just 2 bytes for a real instruction. So you need way less memory. If, for example, you just want to load one register value to another, it's just as simple as using 2 bytes and not having to use 4 bytes all the time. So it's just a memory saving method. I will now quickly scroll through all this interrupt vector stuff by pressing 3 times D and pressing the arrow down. This will take a few seconds. And based on how the data looks, I know where the interrupt vector stops. It could also be done by using the data sheet and checking out how many interrupt positions we even have. But let's just quickly do it that way. And you can now see that the data looks unrealistic. This address is way out of our memory region, so we know that this is not an interrupt vector anymore. And I press the U button to undefine it again. So this is now basically the reverse engineered in quotes interrupt vector. And what we want to do now is to double click on this address and it will jump to this position. Only that we now are at the D5 region, but since it's an uneven number, we know it's some code, and this is how ARM says we are now running thumb code or not. So we need to move one further up to the D4. And here we can now do right click and click on code or like so. But even better, we can click on P for procedure. So it will know that this is our real instruction we want to start from. And we can already see that it did detect some of the memory. So it's a new sub where it's jumping to. Like here we have another region where it's doing stuff and so on. But this is not good to start reverse engineering, as we still have like a lot of yellow stuff, so undefined stuff, and just like minimal detected functions. To go further, we want to go to each position that looks like code. It's really most of the time trial and error. So for example here I will also press P and it will continue to define the functions it has seen. It will go into the next function and into the next function, and it IDA is quite good at detecting all the function, and you can see how much blue function is already available. To now not have something left out in the middle or such, I will go from position to position, and if it looks like code, I will go there and define it as code. Scroll down to the next empty section, always looking that we have even number, as only that can be code. And we'll just continue now to go through the complete file, and this will just take a few minutes. I will fast forward this for you. So, and sometimes it happens that you have a function where you like press P, but it does not decompile. So then we can do the code sections or press like C, and it will also start to decompile it. It's different on each file, and you may want to revisit it later. And it could be also that this is just simply no code, but it depends on what file you have. In this case, it is code, so I'm also decompiling that part, as it just looks like it. And you can also, of course, always redo stuff later if you see that it's wrong or not fitting into each other. Also, we have sometimes here some obvious strings. It's like on and off. And there you can go into, or you can press just A, and it will define it as a string and another one. And every now and then you come across something like that, and then you have some more obvious parts in the firmware to reverse later to just know where you are. Especially here we have a display and we see some strings happening every now and then. And if we find them again here, we know what the firmware is doing at that point. So we know it's writing to the display, for example. Here in this section, for example, we see that we have some strings, but then we also have like these fields, which looks a bit strange. But based on that the firmware also supports Chinese language, I suspect these to be the Chinese characters just saved as a ASCII string or just in their encoding. So as just based on that they are near these sections. And it's quite visible. So you have like these values next to each other. Here we have something that looks like a string again, like it's milliseconds. And it's basically, or it looks like here is a gear in English and here would be gear in Chinese. At least it looks like it. And you can also see some nice names we can use later. Okay, and here's, for example, one section which looks strange. We have like ARM code, but strings above and strings under it. And this code could be valid, but in this case it's not. So we mark it and just undefine it. And now it's also clear that this is just, yeah, these are just strings again. So these are the language settings as it seems. So the function that is calling them here, these are the reference to this position, most likely takes care of the language settings. But yeah, just as a suspicion right now. And every time you come across like to such positions of memory, it does not look like code. It's like many zeros after another is no valid ARM instruction. So you know this is no code and here's no code. So it's most likely these are really like variables, but no code you could decompile. And it's like very dynamically looking into how it looks just to prepare the file good enough. So we are nearly at the end of the reversed or decompiled code. And from here on we can see, okay, there are a lot of zeros. This very much looks like the end of the firmware. And also if we take a look at this data, it does not even look like valid code anymore. So you can see a big difference to the other stuff. And what this is, it's most likely the font that is saved in memory and also the boot image, for example, or the running image of the display. So if we scroll down to the bottom, we see there's not much else anymore happening. And this is basically our complete firmware prepared to now reverse engineer it. Yeah, one other step we can do beforehand is do a right click now on these on the reset vector table and define these not anymore as just numbers, but as pointers to the function. So we do a right click on every of these functions like so. But what we can see here is that there are a lot of same values except for this one, and this will be important later again. If there is the same number all over again, we know it's basically like unused code, and we can ignore it more or less. This is like a placeholder in ARM code to not run into wrong code. But yeah, also these null subs are really just like an endless loop. So we know these are unused too. And if we take a look inside here and also reversing or decompiling it, we see that it's just doing a knob here and then also going in the loop. So based on all of this, we can already see that really only this interrupt vector is really used at all. Of course, also the first one, which is the reset. So we call this reset ERQ. And so this is where the chip will boot. And this is the only other one really used. So very likely this is a timer, which is called every defined moment. As we know, the Spot Welder is doing something very precise timed. It cannot be like a button interrupt or a GPIO interrupt, whatever. So we know this will be a timer interrupt, and we can already rename it as a timer ERQ, so interrupt routine. But that's for later. Let's first now just click here again. And we can now press F5 to go into the decompiled view, which looks like this. It's basically a pseudocode generator and is just the best thing in this world to reverse engineer stuff. We can click into functions like we would use if we code something new and see what these functions are doing. So for example, here we see stuff happening at this region of memory. It's like setting values, and based on that this is like the first function called at all, it's very likely that these are just clock settings or just basic chip settings to get it up and running. Then we have also more of these, which is mostly just like getting the chip starting into a good mode. If you do a full reversing, you want to look into that as well, but we only are interested in flipping the screen. And if we click into the next function here, we see that it's initializing a lot of variables. We see that these are variables as these are in RAM region. And we see that there are some functions happening. It's doing a while loop until something is set here to the correct value. But after that, we have this while loop. And what this is basically our main function, as if you would code something new. So we can rename this function to main, as it's quite obvious already. And we want to just take a look into some functions, follow around, and just get an overview of how things look. And directly what comes across here are these functions that are called every now and then. These are, as suspected, the display driving functions. So you have like X and Y coordinates, some variable you want to write there, and some rotation or color values that is set. So it's basically you are already seeing C code, pseudo C code of course, but you can directly see what is really happening if you follow this around. But for example, for this functions, or for this function itself, it's quite obvious that this is some LCD printing, whatever. I will now leave it blank here as it's not clear what it really is, but if we take a look inside, we can see it's doing something at the beginning, and if we click here in as well, we see it's some kind of loop where it's just counting something down, so it looks like a delay or so. It's unclear, but we just go through these files or parts, and this is looking like something like a memset function or so, but unclear. Let's just browse around a bit. We have here again this counting down function. It's again looking like a delay, and this again looks somewhat like a mem copy function, a mem set function, something like that. But in the end it calls these two functions here, and if we go in there, we see just more stuff, more functions, and we just follow around a bit. What we now here see is what it's doing with these A1 and A2. These are the variables this function is called to, and by going back one function, we can see here that it is used that way and that way, and we know that the first two functions are the X and Y coordinates, so we know that like the first one is here called and the second one is here also called. So we know these are the X and Y coordinates, A1 and A2, so we just rename it to X and Y, and we can see that it's also here being called with X and Y, and also X plus something and Y plus something. So based on the knowledge on how the display works, which we also can look here, it's like the datasheet from a random ST7789 display. We know that these first, these 42 and 43, if we convert this to hex, is 2A and 2B. And these are basically the Windows settings functions of the display. So you say, I want to start my region of memory, I want to edit on this display, and the end of this region. And after that you say to C to activate the writing to the display. So we know that this is basically like the writing of memory function. So it initializes where to write in memory, and after that it will write into the memory the correct data, like the string or stuff. So let's go back into this once more, and we can already rename this LCD window setting or something like that. It's really up to you. But what we also know from this is that this is the command for a display, and what comes after it is the data for the display. So if we click in here, we see, okay, it's not directly using this value, but it's an integer 16, so it's 2 byte. But normally such a function would only write 1 byte. But inside we can see that it's writing 2 times one function, which then again is writing to the SPI bus to the display. So we know that this is an SPI display as it's the ST7789. So we can already write in here, or let's also call it SPI, LCD SPI data. And what we also know is that this function does not return anything, so we can remove the return value. And if we now repress F5, it will decompile this functions, and as it knows now there is no return value, it will also remove the return from this function again. And this same can be done here as well. Looking inside of this, we notice that in the data command, it's also calling this function. So that means there's something wrong, and it would need to be called just like SPI transmit. So it's changing every now and then. And based on what I know about the display also is that we need to enable it via the CS pin. So it's the chip select pin from SPI. And most likely this will be done before and after writing. So here it will pull down the chip select, and here it will turn it up again. So we can rename this to GPIO low. And the other function, let's rename it to GPIO high. These are of course all just conclusions, and we can later just verify it, but it very much looks like this already. And if we here also again press F5, we see that inside of the transmit function it's also doing this low and high. What this means is that we have the CS pin being handled inside of the transmit function, and before it does another pin low and high, which means it is the DC pin. So it's setting if it's a data or a command that is sent via SPI. And so we can rename this to LCD SPI command. As we just know, this must be a command. And this can now be LCD SPI data, but since it's 16 bits, we name it data 16. And this already looks kind of like real code. So if we press F5 again, we could rename this also now to X and Y and such. So this already makes totally sense to be valid. If we now scroll around a bit, we have this neat function in IDA to do a right click and to jump to X references. So we can see where this function is called, at least where it's
decompiled already. If the if IDA does not know where a function is, it can of course not see where it's the solution is. But what we can see here is like there is one function which calls this display or this SPI command function by a lot. And if we go into it, we see it's basically like a lot of writing to the display. And based on the knowledge again of how this display works, this is the initialization of the display. So it will set what resolution the display has and such. What we can first see here that it's also pulling one GPIO low and high again. So we know that this is the reset pin. And also again, based on the knowledge on how this display works, I know that there must be a delay between the low and high part. So I know that this function here must be a delay milliseconds function. So we just call it that. And so this code looks better already. And this is now then inside calling another function which is called with 1,000. So this must be something like delay US, so microseconds. And also we most likely know that the delay function is not getting anything back, and also this function will not return any value, so we can remove it again. And already this code also looks quite neat and nice. So if we now do the same here, pressing F5, we notice this function is called. These registers are basically inside of the processor some special registers. Like here we can see that the 12C00 is here 12C00. So it's here named timer 1. So that we know that this is doing something with timer 1, like starting timer 1, stopping timer 1, whatever. So this is how you also know what these registers are doing. And also if we look here at this 48000, we know it's that's not fitting complete. It's because it's 4800. And let's hope we can find it. Yeah, here. So we know that these 4800000 is GPIO A. And that way we can also know, okay, this has definitely something to do with GPIO. Another stuff here is again some initialization of something. This most likely looks like it's initializing the SPI data. If we take a deep look into it, we could follow it, or it's initializing the GPIOs to the correct stuff. But we want to now look inside of this initialization function. Since I know the display has this register 36 in hex, where we can set the mode how data is entered into the display. So depending on how this byte is set, the entering of memory is rotated. And rotating is really what we want to do in the end. Since these are now decimal values, we want to change them to hex. We could do it by right-clicking and converting them. But if we change just how the function is called by changing it to an undigned char, IDA knows this is a hex value and it will convert all to hex. And we do the same on this one. And what we can see here is that it's just calling the transmit function inside. So this must be the LCD data function, but not for 16 bytes. It's just for 8 bits, sorry. And here again, we do this unsigned char setting. So it will also convert everything to hex if possible. And scrolling down a bit now, we see something interesting here. It's this command 36. And voila, it's exactly what we want to look out for. But let's take a look. The entering of this value depends on a variable. So this seems somewhere in the firmware needs to be a function to rotate the screen, at least based on what it looks like. So we can already rename this here to LCD rotation. So we know this is basically defining at what rotation the LCD is. And we can then look inside where this is handled. And we can see here that this is just loading from it, this value. But here are also functions where it is writing to this value. Let's just start by main. And we see, okay, at boot it will be just set to 0. So it will start at a normal rotation. Then let's take a closer look into the next function here. And here it looks like, okay, it's loading the value from another memory region. It's copying like a lot of files from somewhere else. And by converting a few of these to hex, we can see that this value is basically a very human readable and looks very much like a magic number. So it's a value to prove that another value or a value is correct. And it's checking if this memory region has this value. And if we now check into the datasheet, and hopefully it's there somewhere. Okay, it does not look like it's available. Oh, it's available inside of this flash somewhere. So, aha, it's loading some values from flash, but that means these values could be changed somehow. And this looks most likely like an EEPROM. So, like it saves the settings in flash, and on next boot, let's see where this where this function is called. Okay, also in main, but quite low. Okay, so we know it first initializes it to 0, but inside of this function it will set it to value from flash. So okay, that means it will just load it somewhere. But that also means it must save it somewhere first hand. And also we can remove the return value and just leave it that, and just recompile it here to have it look nicer. Okay. But let's see, we know this function is called somewhere else also in this part here. And let's take a look what this is doing. So, okay, it loads it's checking if the value is 0, and if it's 0, it will write a 1 to it. Okay, so this means it's basically like a toggle function. So every time this function is called, this value will toggle. And by looking into the next function here, and here also again a bit deeper, like here, we see, aha, it's the LCD init function again. So let's also call this init pre. So as we know, inside of it, it will initialize the screen again. So this looks like, it's basically like setting this value to the other one, so rotating the screen, and initializing the screen again with the new value, so it rotated screen. So we know that this function must be called to rotate the screen. And also here again, sometimes it looks like valid code that this has a return, but it's just either trying to decompile it as best as it can. But by seeing that this value is like returned, but here set again to 1, it just makes no sense. So we can remove it again. And it again looks way nicer that way. But okay, let's rename this function and then rename it to LCD toggle rotate. And let's take a look at where it is called. Okay. So it seems that no one is even calling this function. So could be that this is just a leftover in the firmware and just not used. Or it's somewhere called dynamically. And this dynamic calling is like loading memory addresses at runtime, so IDA does not know where it is called even. So okay, let's think about it for a while. But yeah, if we scroll a bit around, and this is just fast forwarding for you now, seeing this function here, and let's decompile it once more. Looking at these values and maybe even entering one function, we see that the passed arguments is here called as a function. So this means that the way it works is like the address passed to this function is dynamically called, so it's exactly what we are looking for. And now that the function is known to IDA and knows that it's a void or a function, we can press F5 again to decompile it again. And aha, let's take a look here. So we know this function is called whenever it is inside handled, whatever. So first of all, let's again remove the return value. And even now it looks like some nicely formatted code. And we see that it's doing a switch code on a value laying at this address but +1. And it's handled as a byte. So let's just reset this type also to a char, so it's just 8 bits. And as it's called at another memory address, it must be some kind of array, so we also press this, and it's again looking a bit nicer. So what we can see is here that whenever this function is called, it looks into the memory region 1 up of this address, and based on what the content is, it will call the functions passed to it. And looking here inside of the other one, okay, it's the same, but we can press F5 to make it look nicer. So again, we see here it's calling it with this address and with this address. Oops, sorry. So we can rename this like dynamic calling of function trigger, whatever. And here again, but let's call it 2. And then we know that this function here is this rotation. It did rename it for some reason, but let's rename it back again to have it look nicer. So okay, we know here are 2 other functions and here are 2 other functions, but let's take a look where this memory region is used, or more likely not this. This is now again the just raw view of data. But since we are interested in the byte after it, we can rename this again and trigger LCD rotate. So it can be called this way. But we also see that it's used here again and with the same function. So let's call this dynamic function calling or something like this. So you know what it does roundabout, and here again we also are more interested in the value afterwards. So trigger LCD rotate 1 can be called. And if we now do a right click and also look inside what it is doing, we come across the timer interrupt function again, renamed earlier. And if we decompile it, we see that this function is basically called here inside, or set this value to the function that it will later call. And we know that the 1 and 2 is a different function, but the 3 is our LCD rotate function. And if we take a look here, we can see that it's using both of these variables for whatever reason. If we scroll up here again, we can see it again. And let's think about what it does here. Let's just look. This timer function will most likely be called maybe every 100 microseconds or such, or maybe even every millisecond. And it's then just simply checking for some variables that are flagged. And here we can see that it is checking for this value and shifting it by 15. And based on the knowledge we gained earlier, we know that this is a GPIO region of memory. And scrolling back further down, we see another GPIO region, but this looks like from port B and not port A from the GPIOs. So we know this is checking something on the GPIO states. And based on how the firmware works, and we know that there is no other interrupt for buttons, we can suspect that these are basically buttons. And if we now look inside of this, we can first look into the upper section and see that it's checking at what value this trigger is right now. And if we follow it further down, we can also see that here it's increasing this value every time it is called. And let's scroll down. It's here increased as well. And checking the function trigger 2, we can see that it looks basically very similar. So this looks like some timing handling of how long a button is pressed or is not pressed. And depending on how long it is pressed, or it was pressed, we see that it is either calling function 1 of this dynamic function 2, or function 3. And why they are calling them not directly here is because this is inside of the interrupt and you want to spend as little time in an interrupt as possible. So they will just flag the function here and it will be called in the main loop to not to stay in the interrupt for too long. Okay, so but what does it mean for us now? So we know that this function 3 is our LCD rotate. We want to find out how it works, and we see that it's called in both functions. And also we can see that it's basically like somehow related to both of these values together. And you may have guessed it already. This means theoretically, if we press both buttons of the Spot Welder at the same time, it will then trigger both of these flags. If it's timely correct, of course. You will never press both at the exact time, but it should be enough to just press them both at once for a while, and it should then trigger this LCD rotate inside of this main function to then inside of this LCD rotate toggle this value, reinitialize the LCD, and go on with its way, and just removing this flag again. And as you have guessed it already, this is exactly what it's doing, and this is the solution. It's funny to see that it is implemented in the firmware, but so far I have seen it nowhere documented. And what is also possible now, of course, to just do further reversing of this firmware, write an own custom firmware, etc. pp. This is basically now open to dive deep into it, and very dynamic to all other firmwares as well. So even if you have 8051 core code or whatever, x86, etc. pp, and so on and so on. So as we have the solution, we can finish it up and go our way.
Oh hey, it's you again. So as teased already, we know the solution, what it is. We turn the device on. the screen is this way up. And if we press both buttons at the same time, if I am able to do it with one hand at all, like so, it's rotated. And if we do it again, it's rotated again. So based on the reverse firmware, we see an undocumented feature. Even while it's existing, it's not meant to be there as it seems. And it's quite the fun challenge, fun little gadget. It took me about 1 hour to get fully into it and reverse engineered that far, with also getting you through the steps of it. It's also just like the time you'll see in the video. And that's it. You will most likely never see this again in any video, and wish you a great day.